continuing with 2015 locals. We have 21 through 30 now. Basically, the first one's a thermo question. When it tells you that it's a well-insulated cup, it's hinting at the fact that what's inside the cup and the cup itself is a closed system. So however much heat that the gold loses is however much heat that the water gains. So you can say this value of the water is equal to this of the gold. Obviously you would plug in different values, but I'm just not showing subscripts here. You need a negative sign on one side just because one side is losing heat and the other side is gaining heat. How you could compensate for that is, so here I have the temperature changes listed as 83 minus x and 22 minus x, and then I have a negative sign to compensate for that. If it's easier for you to think about it like that, where you have the number and then minus x after, then definitely put the negative sign. But if you're just thinking about final minus initial, then you can do 83 minus x in this one, and then you can do x minus 22 here, because that's technically final minus initial, and then you can get rid of this negative sign. But the rest of the steps I wrote out are actually with the first method I showed, not this one. So basically, if you solve it algebraically, you get x equals 22.7 degrees Celsius. 22, which one has a positive standard entropy change? Okay, so this one, you go from a liquid to a solid. Your particles have less freedom of motion, so entropy change is actually negative. This one, you go from 2 moles of gas to 1 mole of a solution, so less freedom of motion. This one, you have 1 mole of gas, 2 moles of solution, and then you get rid of the gas and you make some solid, so once again, more restricted motion. D, you actually go from 1 mole of gas to 2 moles of gas, so it's more, well, not necessarily more freedom of motion because they're both gases, but your particles can exist in much more different conformations. Not in the technical sense, but there's a lot of more different ways that the particles can be split up. 23, given this stuff, what is the delta H? Okay, so we have to utilize Hess's law here. It's basically just addition. Let's see, so we have 2F on the product side, 2A, B, and D on the reactant side. So the only elementary reaction that includes B is this one, and we know that 1B has to end up on the reactant side. So we multiply that reaction by 1 in a sense, but obviously we're not changing anything about it. And we know that this elementary reaction gives 1A to the reactants, but we have 2A in the overall reaction, so we also need to multiply this thing by 1 in order to get 2A on the left side. And that means we have 1F on the right side, but we have to end up with 2F. So we have to multiply this by -1 in order to reverse the reaction. So that would mean we do -35 plus +20 plus -15. So that would be -30. Yeah. 24. Okay, looks like we're using the Vantov equation. So there's a lot of different forms that you'll see this equation. But, I mean, they all look very similar, but this one is the Vantov equation because it utilizes reaction, it utilizes capital K, so that's what separates it. So you have this and then this component. Okay, so we're given delta H, and we're given both a temperature and its corresponding K. So we can solve for K at the other temperature. We're going to say Ka is actually K2 here. So if we plug stuff in, we have, that's our given Ka value at 25C. And remember to always substitute temperatures as Kelvin. Did it say it's negative? Yeah, so actually the negative is included in the equation, so if you have a negative delta H, you need to include another negative. Here you would have 1 over 60 plus 273.15 because we're in Kelvin, so 333.15. And then you would have 1 over, there's a point here, and then that one occurred at 25, so that's 298.15. Sorry for going off the page. So if we just calculate the right side of the equation, we end up with, hold on, we end up with ln of Ka over the other Ka at a different temperature is equal to negative 0.602. So then we raise everything base E. That means Ka over this is equal to 0.548. And then if we multiply those two things, we get Ka equals 0.00416, which rounds to 4.2 times 10 to the negative third, so we choose A. 25. Okay, so for questions like this, you do not need to know the rate law. It's not about the rate of reaction. It's simply coefficients. It's stoichiometry. So they put it in the kinetics section to throw you off a little bit, but it's literally just multiplying by coefficients. So here, ammonia is consumed at half, I don't know how to say that, but half a molarity per second. So what rate is water formed at? We have a 4 here, we have a 6 here. So water should be formed at 1.5 times the rate that ammonia is used. So 5 times 1.5 is 7.5, and if we scale that down, it's 0.75. 26, rate of decomposition. Okay, so rate is equal to K H2O2. Technically, it is H2O2 to the first, but I'm just omitting that because it's understood, because it says it's first order. So it says that the rate is equal to this value when H2O2 is at this concentration. So we can just find K by dividing. Then we get 3.22 times 10 to the negative fifth, which would be 27. Okay, that's just memorization. I'll just quickly go over. In USNCO, really only 0 first and second order things are covered. For 0, you would simply have this is linear over time. For first, you would have natural log is linear over time. I should have left myself some space there. For second order, you will have that 1 over the concentration is linear versus time. And how that affects half-lives is that the half-life for a first order reaction is constant. So that's when we deal with like nuclear decay. The half-life for a 0 order reaction, I'm pretty sure it gets half as small every half-life you progress. I could be mixing up 0 and second order, but I'm pretty sure I'm not. And then for second order reactions, oh, hold on, yeah, I think I am mixing it up. So for first order or 0 order reactions, half-life doubles every time you progress through another half-life, and for second order reactions, half-life halves every time you progress through another half. Okay, no. When I say that, it's wrong. This is 2 times, this is half. I'm gonna move on now. 28. Okay, so this is what I was saying. Any radioactive decay that you have, that's first order. You can just automatically assume that. So then if we put the integrated rate law equation, We're looking for, well, first, ln2 over k is always equal to your half-life for a first-order reaction. So we're given half-life, and we just need to find k. So then k would equal ln2 over 8.02, which gives us 0.0864. That's our k. And then we can progress to the integrated rate law. And then it says actually the cool thing about first order reactions is that you don't need the specific concentrations. You're just decaying to 80%, right? It says, oh, no, you're decaying to 20% because you want 80% to decay, 20% to remain. So you would actually have 0.2 here and you would have 1 here. But if you subtract logarithms, it's technically just division of the operator inside. So you would just have ln of 0.2 over 1, which is 0.2, is equal to negative this. So then your t, if we calculate ln of 0.2 divided by, it will be 18.6 days, which is 19 days if you round up. Okay, so for this reaction, the reason it's not a pH meter is that well, obviously these don't have any real effect on pH, but neither do Br- or Cl- because they're conjugate bases of strong acids, so they don't really attribute to any pH changes in a solution if they're just by themselves, unless they like precipitate something that would otherwise do something with pH. Here, spectrophotometer would work because Br2, I'm pretty sure is like red or something. Cl2 might be colored, I'm not sure, but I definitely know that Br2 is colored, so a spectrophotometer would work. Okay, reversible exothermic reaction. What is the effect? Alright, so anytime you increase the temperature, if it's an Arrhenius reaction, which pretty much for USNCO you can assume, if you increase the temperature and it's an Arrhenius reaction, meaning that activation energy is positive, the rate will increase, and that's what the Arrhenius equation describes. So the rates got to increase. Both forward and backward rates will increase, no matter whether it's endothermic or exothermic. So anything that says little k decreases, you cross out automatically. And then here, if I just draw this out, this is like a very simple exothermic reaction. Heats a product. If I increase the concentration of a product, so I increase temperature, increasing heat, my reaction will respond according to Le Chatelier's principle by shifting towards the reactants. So that means K will decrease. This is big K. So that's why it's D. Alright, next video we'll do 31 through 40.